All right, so this is 6-1. It's a one-day lesson, but there was a lot of material in 6-1. And we're going to begin with the PowerPoint, okay? So, first you got this, ready? We have this function, it's quadratic, x squared plus 3, then the derivative is 2x. Yes, that's pretty straightforward, that's just the power rule. But, the paragraph could be x squared take away 5, and the derivative would still be 2x. What are we talking about? That's the Pringle scenario. Because both of these functions give you the same derivative. They have the same shape. And the constant determines where it sits in the Pringle scheme. That's what we're looking for. So when you back up, you have an issue. When you go from right to left on the H chart, you're trying to go from the derivative to the parent graph. We don't know what the constant is, because it would have differentiated to 0. What do we do? Yeah, we identify it with a C, which is really what? It's really K. Doesn't matter what letter you use, because if you think back to doing transformations of H to the right up K, that's what this C is. It's how high up or down. It's a vertical translation. So you need some information. So in this problem, it's an initial value problem. You know the derivative is 2x. So we take this question and we do this. We build an H chart. Our H chart looks like this. We're told that y prime dy dx equals 2x. Therefore, when we do the power rule in reverse, we would get y equals 2x to the 1 plus 1 divided by 2, which is x squared plus c. Understand what's happening? In the power rule in reverse, which is awkward for like 2 days. And after those 2 days, you need to be able to do this. But they're telling us it goes to the 0.14. Yes? So if I put 1 into y equals x squared, the output's a 1. The y output's a 4. So I have to take this graph and slide it 0 right or left of 3. So that 3 is your k, which is the same thing as your constant, which is c. That constant is the vertical slide. Okay? So nobody can do this problem. Nobody can go from right to left on the H chart and find a parent graph unless they are given more information. You have to be given one pair of coordinates. The parent graph for this one. Okay? Now, slope fields, this is new. This is on the AB test and the BC test. And the question that we're going to take you to in the homework problems is what the slope field question has looked like in the past if it's on the AP test. We're not complicated. The only problem with the slope field question is you feel so confident you can do this that sometimes people spend too much time on it. It's not going to carry that much weight. You can't say I'm going to produce the best slope field the College Board readers ever read, because if you do that, you're going to run out of time in the rest of the test. So here's a slope field from the problem we talked about. Y equals 2x. I'm sorry, y prime equals 2x, yes? So we're going to build a slope field. What does that even mean? You put in the ordered pairs. So if we start with the origin, you're putting in both ordered pairs. Oh, sorry, you're putting both orders. 0, 0. Now what? The derivative only depends upon the x. So 2 times 0 is 0. What does that mean? At the origin, the slope of the curve would be a 0. So you draw this segment freehand with a slope of 0. Then what? Well, you notice that it doesn't matter what the y is. On the y-axis for this function, all the slopes would be 0. So you just draw them like that. And what? We go to x equals a different value. So we go to x equals 1. Well, with x equals 1, all the slopes would be 2. Well, does that look like a slope of 2 to you? You don't have to worry about it being that precise. We're just trying, college board readers looking at you when you have the correct SIG. Now, this is way easier than the problem. Homework, you just trying to get an idea what's going on. If you put positive 2 in there, you'd have slopes of 4. So what we're looking for is this slope more pronounced than that slope. We go to x equals negative 1. Slopes are negative 2. X equals negative 2. Slopes are negative 4. There is your slope field. What does that mean? It means it's like a maze that will direct the parent group. The parent group has a synonym. So we know that the derivative is 2x. Now, ready? This is a little awkward because what do? They came up with a different initial condition. A different initial condition. Instead of 1, 4, it's 1, negative 2. Even though it's the same derivative. So you go to the point, 1 to the right, down 2. They're telling you that's on the graph. So when you go 1 to the right, down 2, from there you go up because that's where the slope was channeling you. You've got to be careful. The slope field, the initial condition may or may not be the vertex. But you can't just say, oh, I'm going to go here and then push my way up there. That's what it looks like. Okay? So it's that way it's going to move down 3 as opposed to up 3. So, you get a problem like this, ready? I want the area under y equals x squared between 1 and 4. Why? Because this is the derivative. X squared is the derivative. The height times the width, add them up, starting at 1 and ending at 4, would give you the change in the position of the parent graph. What would the parent graph be here? Look at your pencil, let's go. What's the parent graph? X cubed over 3 plus a constant. Yes? Because then when you turn around and differentiate x cubed over 3 plus a constant, that will differentiate to x squared plus 0. So we want the area under this to tell us the change in the parent graph between 1 and 4. So we get, there's your x cubed divided by 3 plus the constant. But what happens? The constant's going to subtract to 0 every time. We would get a numerical answer of 21. What's that telling you? The area under the derivative is 21 square units. it means the change in the parent graph between 1 and 4, the change in y was 21. Delta y was 21. If you just had this problem and there's no limits, that's indefinite integration, and your answer would have to include the plus c. Okay? If you do this problem in May, and you omit the c, you get errors. So what's the point? It doesn't matter if it's definite or indefinite. You should put the c there. Because it doesn't hurt you for definite integration, because the c would subtract to 0. But if you omit it and it's indefinite, you will not get full credit. Now, we are going to do this. We're going to show you this first. There's 3 components to this lesson. One is initial value problem. Another one is slope fields, and the third one is Euler. This, you're watching this video, and you're an AB, but fast forward to this, because Euler is a BC topic only. So what Euler is repeated use of linearization. Well, you know what linearization is, we did in chapter 4. It means that you leave the parent graph and you travel on the tangent. And if your trip is not too far, your delta x is small, then the value of the tangent graph will approximate the value of the curve. What are we doing here? Repeated use of that. So this makes sense to you. I go over here and I build the table. In fact, I'm going to put it over here so people at home can see. All right, so here's our table. We have x, we have y equals, we have dy dx equals 2x. That's given. We know that at 0, the y value, the height is 1. But since we're approximating, we can say this. The change in y equals 2x dx. Right? This is not accurate. Anytime you do that, you quantify dx, it's automatically estimated out. As long as you understand that, it's fine. So multiplying both sides of this differential by dx automatically disqualifies you from having instantaneous change. We're not interested in instantaneous change. We're interested in this case in an approximation. So we have 0, 1. Ready? Here's what we're going to do. They're telling us in this case, in this example, that you haven't seen on the PowerPoint yet, that dx equals 0.5. So we're going to make changes here. 0.51, 1.52, 2.53. We're going to draw these segments that are going to be 0.5 as a base, 0.51. Right? So what happens? We have this 0.01. So the derivative is 2 times 0, which is 0. The slope here is 0. What's the change in y? 0 times 0.5. The slope in y, the change in y is 0. So when I go to 0.5, I would still be at 1. There you go, over this again. Look what happened. Here's the change in y. 2x times 0.5. 2 times 0 is 0. 0 times 0.5 is 0. So dy is 0. Your change in y is 0. It was 1, it stays 1. Now we go to this point, 0.51. dy is double x, 2x, 2 times 0.5 is 1, times 0.5. So that's 0.5. So this goes, these are all, ready? These are all 0.5 for dx. So this would go to 1.5. Now what? 1.5. Double that. That's 3. 3 times 0.5 is 1.5. This would be the point 1.53. One more. We put 1.5 in here. We double it. Right? And we get 3. 3 times 0.5. Did I do that right for this one? If I put 1 in here, I get 2. 2 times 0.5 is 1. Sorry. So this was 1. So this went to 2.5. I got ahead of myself. I put 1.5 in here, I get 3. 3 times 0.5 is 1.5 plus this takes you to 0.24. On the PowerPoint, what happens? Here it comes. You just connect those points. We'll go as far as 2.4. You connect these points here. 0, 1, 2, 0.51. 0.51, the 1 to the right, up 1.5. And you've drawn this series of linearizations. And what happens? It's a slope field. Because here comes the curve, it fits inside it. So, we'll go over how to do this. It's not difficult. Okay, if you get an Euler question, in May, it's a layup. You just have to conceptualize what you're doing. You have to understand, the test is for 6 months, and this is not challenging. All right? So, to the PDF. Here's example 2 in the book. Example 2 says, this is an initial value problem. Remember 3 things today. Initial value, and we're going straight through the 10, 20 because there is no exit. Initial value, slope field, then what? Here's the initial value problem. Example 2. Find the solution. We're given the derivative. The derivative is dy dx. It's e to the x, which is negative 6x squared. But you need that to go to the point 1, 0. The parent of the derivative. So we come over here. We're going to anti-differentiate that. This is the derivative. E to the x is its own derivative. Power rule reverse for this. So we get e to the x, subtract 2x cubed plus some constant. So I drew the picture for you. Here's the graph lamp. And then I put in brackets, -3, -2, 1, 0, 1, were the constants. And then you can see how they all fit in here like Pringles. But which one goes to the points 1, 0? That's what we're trying to find. So we come over here, we do this. If I assume the constant 0, and I put 1 in here, you get e subtract 2. You don't need e subtract 2, you need a 0 there. So we have to shift the graph down by a magnitude 2 subtract e. When we add to this, it was a 0. So 2 take away e is our constant. That gets added to this. That would be our parent graph. This graph has that derivative, and this graph goes to the point 1, 0. So that's staying up there as your model, and you're going to problem number 13. All right, you be here. How will we reverse? We get 7x to the 7th divided by 7. Subtract 3x to the 3rd divided by 3 equals 5x. The 3's are reduced, the 7's are reduced. We get x to the 7th, subtract x to the 3rd equals 5x for some constant. The initial value is 1, 1. If I put a 1 in here, you get a 5. So in your T-chart, if the constant were 0, you would get 1, 5. You need to have 1, 1. So you slide the graph 0 right or left down 4, so it goes to the point 1, 1, and you would have this u plus 4 equals that, or mu equals that, which is a negative 4 to the tail end. Okay. So now we're going to go directly, what we usually did on the PowerPoint, go to page 328. On page 328, this is exactly what this looked like on the AP test. They gave you this grid. But we're going to do problem 31. You have this grid here. And for 31, they want you to draw the slope field. Like I said, this is where people get carried away. Because it's not difficult, and they go overboard on their explanation of Fox movement. So they give us these points, and we're just going to do the corner points. And the rest of it, ready? You can do 2 of the problems are homework problems, 30 and 34. You need reinforcement what we're going to do there. So we take these corner points. Let's start with 1 to the right up 2. So at 1, 2. Ready? This is going 31. At 1, 2, the slope is 2x plus 1. Now this problem's different than what was on the PowerPoint because it's derivative. The first time you see this depends upon both x and y. So the coordinates are 2 to the right up 1. 2 times 2 is 4 plus 1 is 5. It means the slope is 5. You draw a line segment through there. It's approximately 5. What do you need? Okay. Now we go to the point 2 to the right down 1. So 1 to the right down 1. 1 to the right down 1. 2 times 2. 2 times 1 is 2. Plus a negative 1 is 1. That would just be a slope of 1. See the PowerPoint, everything in the same x value, I can see slope. This file. And then if I can get an angle like the PowerPoint, I'll just get it. We go over here. 1 to the left, down 1. 2 times negative 1 is negative 2. -2 plus a -1 is -3. Slope of -3 from that point. Then we go to 1 to the left up 2. 2 times a -1 is -2 plus 2 is 0. That one has a slope of 0. So we did 4. There's 12 points. Right? We have to do all of those 12 points and draw the slope field. That would be it. That component of the question. Okay? But a couple of results about this, you need to go to 30 and or 34 to make sure this makes sense. All right, so we're going to go back to Euler. So if you are, again, if you're an AB child and you're watching this video, you're finished. Because Euler is BC only. But if you're a BC child, Euler is important. And we're looking at example number 9. Okay? So for example number 9, here's what you have. There's a picture of the focal base 3.6. You want to see. But the initial value is 2, 0. So I wrote this in function notation because it's kind of cluttered on the table. 2, 0. The derivative is x plus 1. And delta x for this question is 2/10. So on the PowerPoint, delta x is 5. They won't give it to you when you change that. What are we saying? The derivative at the point 2, 0 will be a 2. It's the sum of those two. For now, delta x is 2/10. So what's the change in y? Well, the change in y is multiplying x plus y, the derivative, by dx. If I multiply x plus y times dx, you would get 4/10. 4/10 is the change in y. So when you go from 2 to 2 and 2/10, so that's delta x is 2/10, your y would go up 4/10, from 0 to 4/10. Next point. You start at 2 and 2/10. Is the input and 4/10 of the output. The derivative is their sum, 2 and 6/10. The change in x is 2/10. So the change in y is the product of these two columns. It's 52/100. You add the 52/100 with 4/10, you get 92/100. The x's are going up by 2/10 every time. It's the y values that are changing irregularly. One more. 2 and 4/10 makes it to 92/100. Their sum, x plus y, the derivative is this, multiplied by 2/10 dx gives us dy. We add this to the 92/100. When you get 2 and 6/10, gives us 1.584. The question asks us to keep going until we get this ring. So at 3, the quarter pair would be 3, and the height of 3 decimal places is 3.465. That's what they're looking for. What is the height of the last, the end of the last line segment? Linearize the whole time. So we're going to pause this, leave that up there as your model. You're going to problem number 41, please. So 41 would look like this. 1, 2 is given. So the derivative is 0. 0 times del x is 0. So 1.1 stays in 2. Now what? The derivative is based upon x. 1.1 take away 1 is 0.1. 1/10 times delta x 1/10. Delta y is 100. So I add that to my 2, and I get the 2 and 100. The derivative is 1.2 take away 1 is 0.2. 0.2 times delta x is 2 hundredths. You add 2 hundredths, 2 and 0, 2.01, and you get 2.03. 2.03 would be the height at 3 for that linearized segment. This goes 1, 2, 3 line segments. Okay? So, that's it for 6-1.